Hello everyone. In this video, I will show you how to deploy GPT-Neo AI application on the Akash Network. Akash Network is a decentralized cloud computing platform that aims to provide a secure, scalable, and cost-effective solution for deploying and running applications. It's built on blockchain technology, specifically utilizing the Tendermint consensus protocol. The primary goal of Akash Network is to create a marketplace where individuals and organizations can offer their idle computing resources, such as CPU and GPU power, storage space, and bandwidth, to those who need it. This decentralized marketplace connects buyers and sellers directly, eliminating intermediaries and reducing costs. It uses a reverse auction system, where customers submit their desired price and providers compete for the business. This often results in prices that are 85% lower than other large and well-known cloud systems. Akash is currently implementing the ability to provision and lease GPU's processing power and is therefore launching a GPU testnet to test these features. As you know, now GPUs are most in demand for the AI applications, so the emphasis is on this. In this video, I will deploy a GPT-Neo models. GPT-Neo is an open-source project that aims to replicate the architecture and functionality of OpenAI's GPT models, such as GPT-3, using a smaller number of parameters. It was developed by AI, a community-driven research organization focused on democratizing access to large-scale language models. It is possible to use GPT-Neo with 4 pre-trained models with 125 million, 1.3 billion, 2.7 billion, and 20 billion parameters. The more parameters, the more smarter the model, but it also requires more computing resources. Let's go to the project repository on the HuggingFace platform. This is the model with the largest number of parameters, 20 billion. Other models can be found on the author's page here. Here, you can see all 4 models. GPT-Neo was trained as an autoregressive language model. This means that its core functionality is taking a string of text and predicting the next token. Here we can see a demo of how it works. We enter some initial phrase and the neural network comes up with its continuation. Here the continuation is shown in blue. If you call the generation again, the model will continue all this text. And in this tutorial I will try to make something similar to this demo. Below on the page we can see the description of how to use the model. As we see, it is a Python language script, like in most other applications, but unfortunately, the code example here is very small. It only shows how to load the model. However, the models utilize a transformer architecture and most of the applications of this architecture are used in a similar way, and there are many examples of other models where you can study this. You can also find a more detailed example on the use of GPT-Neo models in the documentation of the HuggingFace platform. Since we need to make a web application, I will use the FastAPI web framework with Unicorn ASGI web server. I will show the completed code to save time and just explain you the most important points in it. Although requests to the server can be sent using curl, it is most convenient to use a web application with a graphical interface. Let's start with it. For demonstration and testing, I created a primitive interface in native HTML, CSS, and JavaScript with jQuery library. We have 2 folders, static and templates. Such a separation of modules is usually done for the FastAPI framework. In the templates folder there is the HTML template of the main and only one interface page. Here you can see 2 files, just the index demo file I use only to show now how the interface will look and work, because in the main template the static files including through a special expressions command. Here is a simple interface. The most important elements are a field for the text, in this case I use the text area element, and the button, by pressing which will create a request for the server to the model. I make the opportunity to launch an application with any GPT-Neo model on your choice. Therefore, in each case, it will be necessary to set up the appropriate name of the model in the page header and the corresponding link to the model repository. Therefore, here written the template expressions with the names of variables that will be transmitted to the template when generating the page. This block is an animation of loading, which is made on pure CSS. You can find many ready-made variants on the internet. By default, we specify display none style for this block, and then in the script when calling the generation we will make it visible. In the head block, we include external style files style CSS and script.js through a template expression. We also include the jQuery library by URL. And another typeit library, also by the link. I use it for a more beautiful output of the generated result with typing effect. This is what it looks like. The static folder contains a CSS file and a JavaScript file. Quick look at Style CSS. There are just a few styles here, nothing fancy, most of it is just for loading animation. Let's take a look at the script.js file. It was written with jQuery. All code is in the document ready block. First, we define the text box and talk button objects. By default, we will insert some test text into the text box for more convenient testing. Next, we create a click event handler for the talk button and try catch block to catch possible errors. And in the handler we write the following, making the loading animation visible. Then encode the input text to ensure that special characters, reserved characters, and non-ASCII characters are properly represented and can be transmitted within a URL. Then, using Fetch API, we made a request to the server to the talk endpoint with input parameter, where we pass all encoded text from the text box. Then, using the JSON method, we parse the response into a JSON-like object. Then, if there are non-error object in response, we output the generated text through the typeit library to the text box. If there was an error on the server, then we display it in the text box in red color. After all these steps, hide the loading animation. Now let's move on to the most important thing, the Python script. First, we import the necessary modules from the Fastapi and Transformers packages. Next, we get 3 environment variables, which we will specify in the deployment SDL file. The first variable max input token length specifies the maximum number of incoming text tokens that will be directly processed by the model. If the text is very large, then it can take a long time to process, especially when computing resources are scarce, but at the same time, the larger this value, the better the model will understand the context of the entered text. And in general, in such applications, there is always a dilemma of how much input data to use for processing, which part can be cut off, or you need to select only the most important tokens and remove the rest so that the model can understand the general meaning of the input data and at the same time not load the system. In general, there is always a huge field for thought and research here, and everything is very individual for each task. In our case, the text needs to be truncated from the left end, as the model works to generate a continuation of the entered text, so the end of the entered text should remain unchanged. The second variable max new tokens specifies how many new tokens the model will generate. The larger this value, the more computing resources are required. It is possible that if the value is too large, the model will also probably start to produce worse results, but these are just my speculations and you need to test everything depending on your requests. And the third variable model name specify which of the 4 models to download. Next, I created a dictionary that contains the names of the models and their name for the title and a link to the repository. Immediately after it, there is a check of the model name entered in the environment variable for its presence in the dictionary, in order to immediately indicate an error if an incorrect name is entered. The next step is to create the tokenizer and model objects. They will automatically download and load the corresponding tokenizer and pre-trained model files for the specified model. Tokenizers are an essential component in natural language processing tasks, as they convert raw text into tokens that can be processed by machine learning models. It allows you to specify the model name or identifier, and it will automatically download and load the corresponding tokenizer for that model. Also, we specify the tokenizer truncation side to left so that the incoming text is truncated from the left end, as I said earlier. Because the default value is truncation on the right. The AutoModel for Causal LM module provides a unified interface for loading models specifically designed for Causal LM tasks. Causal language modeling is a type of language generation task where the model predicts the next word or token in a sequence based on the preceding context. This module allows you to specify the model name or identifier, and it will automatically download and load the corresponding pre-trained model for that task. With Device Map Auto parameter, application will determine where to put each layer to maximize the use of your fastest devices, GPUs, and offload the rest on the CPU, or even the hard drive if you don't have enough GPU VRAM or CPU RAM. Even if the model is split across several devices, it will run as you would normally expect. A library called Accelerate does this. The app variable will be an instance of the class Fast API. This will be the main point of interaction to create all our API. Here we specify directories with static files and templates. Next, we create an endpoint for the main root page. When the page is opened, a template will be loaded into which will be substituted the specified model name and a link to its repository. These values are substituted from the dictionary at the beginning of the script. Then create a talk endpoint that takes the parameter input with our text from the text box. Here we are tokenizing the incoming text, setting the truncation parameter to true so that the tokenizer will automatically cut the beginning of the input text to the length specified by max length parameter, in which we pass the appropriate environment variable max input token length. The toCUDA directive is used to move the tokenizer to the GPU device in order to perform tokenization on the GPU. By default, tokenizers are initialized on the CPU, but if you're using a GPU for your model computations, you can move the tokenizer to the GPU as well to ensure that the tokenization process is performed on the same device as the model. Next, we call the generation method on the model. In the parameters, we pass the tokenized incoming text and the value of the number of new tokens. DoSample and temperature parameters control the generation behavior and randomness of the generated text. When DoSample is true, it enables random sampling of the next token from the model's probability distribution. This means that instead of deterministically selecting the token with the highest probability, the model randomly samples a token based on the predicted probabilities. This introduces randomness and helps in generating more diverse and creative outputs. The temperature parameter controls the randomness of the sampling process when DoSample is true. Higher values make the sampling more random by flattening the probability distribution. This can result in more diverse and exploratory outputs. Lower values make the sampling less random and more focused on the most probable tokens, resulting in more conservative and repetitive outputs. Then we decode the generated tokens back into text. Since this model also outputs all incoming tokens along with new tokens, in our case we need to remove them from the result, since we will add the generated part to the same text box. And since the incoming tokens are truncated to a given length, we need to know what text was actually incoming, so we decode the input tokens too and remove it from the output text. Then we return the answer as a dictionary with the output key, which is then easily parsed into JSON. Using the try-except block, we catch possible errors and pass them as a response with the error key, which will be displayed in the interface. So, all modules are ready. It remains only to install the necessary pip packages and you can try to run, test and debug the application locally, if your computer hardware allows you to do this with at least the smallest model. But if not, then you will have to try to launch already at least resources. Perhaps in the next videos I will show how convenient it is to debug such applications on the least Akash resources. Applications are deployed to Akash through Docker containers. So we need to build our Docker image and push it to our Docker Hub repository. You can use any other repositories, maybe even your own, just the Docker Hub is the most popular and convenient. To create an image, we need a Docker file. Specify the main image from which the container will be built. I am using image Python 3.9, although PyTorch images could also be used, but I install it later with a separate command to install the latest nightly version, since older versions may not support NVIDIA H100 GPUs at the moment. Specify workdir code. Update the apt-get and pip package managers. Next, install the required Python packages. I took this PyTorch install command directly from their site. Then the rest of the packages, transformers is loaded from the HuggingFace repository so that a more recent version is installed. Accelerate, Uvicorn, Fostapi, and a few more packages that obviously don't appear anywhere, but are needed for the previous packages, Google API Python Client, SentencePiece, Requests and SIPI. Perhaps it would be more correct to write all these packages in the requirements.txt file and write the installation command from this file in the Docker file, but in this case it was convenient for me to do it immediately in the Docker file. Then copy all the project files into the container to the code working directory. I copy the files exactly at the end, because if you need to fix something in the code and rebuild the image, then you won't have to wait for all the previous steps with installing and updating packages, and the build will go quickly. And at the end we write the launch of the Uvicorn server, specify the attributes, the file name of the main Python script, specify host 0000 to make the application available on local network, port I chose the 7860. Okay. Now let's create an image. Open the console in the project folder. You should already have Docker installed. And we write the command to create the image, sudo docker build -t, your nickname on Docker Hub, / the name of the repository, I will write GPT-Neo test. And the container version, we will write 0.1. Space and dot, which points to the current directory. Press enter and wait for the build. Sometimes it can take a long time. I'll just speed up the video here. Okay, the image is built. Now let's push it to the Docker Hub. If you are not logged in, then you need to do this with the command sudo docker login -u and write your username. Press enter and you will be asked to enter a password. We enter the password and we are logged in. Now we can push. We write the command sudo docker push and the same name of our image, your username, / GPT-Neo test 0.1. Press enter and wait for loading. Okay, done. Further, for deployment on Akash, you need an SDL file. SDL stands for Software Definition Language, is a human-friendly data standard for declaring deployment attributes. The SDL file is a form to request resources from the network. SDL is compatible with the YAML standard and similar to Docker Compose files. Configuration files may end in YML or YAML. In it, we specify the name of our image. Environment variables, which I talked about when creating a Python script. Specify ports. Our application inside the container will run on port 7860, and at the exit we forward to port 80 in order to enter immediately by the link without specifying the port in the address line. Specify the required hardware resources, CPU units, amount of RAM, GPUs, and storage capacity. Empirically, by launching the application with different parameters, I determined for each model the approximate required hardware parameters. I listed them in the Awesome Akash repository for this app. Based on which GPU we need, we can specify the desired model in the SDL. Just add the model attribute and the name of the model, for example A100. Or several at once, add more V100. And 3090. This 2.7 billions model, they are more than adequate. Placement is map of named data center profiles. Each profile specifies required data center attributes and pricing configuration for each compute profile that will be used within the data center. The deployment section defines how to deploy the services. Each service to be deployed has an entry in the deployment. This entry is maps data center profiles to compute profiles to create a final desired configuration for the resources required for the service. You can read more about this in Akash Docs. Applications can be deployed onto the Akash network using a platform that best suits your needs and preferences. There are currently 3 options: Akash Console, Cloud Moz, and using the command line. I prefer to use Cloud Moz. Before getting started, the Kepler Wallet browser extension must be installed, and with sufficient funds, 5 AKT minimum for a single deployment plus a small amount for transaction fees. This GPU testnet is running on a testnet, so you can request test coins in a faucet. To deploy in the mainnet, you need to buy coins on the exchange. A list of exchanges can be found on CoinGecko or CoinMarketCap. There are both CX and DX exchanges. Go to CloudMoz and connect your wallet. If you haven't deployed yet, you will need to create a certificate in the Settings tab. Somewhere there will be a button, Create Certificate. I already have it created. Then click Deploy and select Upload SDL, or you can select Empty and then copy and paste the contents of the SDL file. Specify our deploy YAML file. We can optionally write the name of the deployment to make it easier to find the right one when a lot of them are launched. And click Create Deployment. We see that you need to deposit at least 5 coins. You can specify more coins if you plan to keep the deployment running for a long time. Click Deposit and approve the transaction in the wallet. Now we are waiting for the list of available providers. Okay, here we see the list sorted by price ascending. We can go to the providers page and clarify additional parameters for us. Select the appropriate provider and click Accept Bid. Confirm the transaction. Okay, now in the Events tab we monitor the status of pulling and starting of our image. We see that image is successfully pulled and container is started. Now on the Logs tab we observe the launch process. At the beginning of the run, the pre-trained model will be loaded, and this can take a long time if the model is large. Sometimes the logs may not be displayed or freeze. Sometimes it helps to simply switch between tabs. As you can see, the model has loaded and the Unicorn server has started, which means the application is ready to go. Go to the Leases tab and find the link to the application given to us. Let's follow the link. Okay, the interface is working. Let's click on the Generate button. Excellent, everything works. Click again and we see that the model continues the existing text. Here you can hang for a long time. The model sometimes generates very interesting results. Perhaps you can even write blogs, books, fairy tales, interesting stories, and much more with it. Don't forget to close your deployment at the end. Click here 3 dots. Close. And approve the transaction. Thank you for watching.